Swayam Prabha. Digital India. Educated India.
All right. If you recall, we are trying to solve the advection diffusion equation as an analytical solution by making several assumptions and modifying our three-dimensional advection diffusion equation, and finally getting onto the concentration, and that concentration, correct me if there is any mistake, was q by pi sigma y sigma z u exponential minus y square upon 2 sigma y square plus z square 2 sigma z square. This is close and this is close. Okay. This is what is the equation we derived yesterday. If you see, okay, in this equation, what was where our source was. Okay. If you again, if I draw the coordinate system, okay, when I am talking about z, okay, z, and this is my origin 0, 0, 0, x direction, y direction, and z direction. Okay. So all z I am measuring from here, right? Okay. So in a way, my source or the emitting source is sitting at this point, right? Okay. But what you will see, most of our chimneys are not sitting on the ground. Okay. Most of the sources are what we call as the elevated sources. So if this is my ground level, my source really, which is kind of a chimney, okay, it's little elevated, okay, well, and when the emission takes place, if you look at the plume in general, okay, that might look something like this. All right. So if I draw the center line of the plume and do this one. So most of the time I will encounter the sources which are not sitting here, but they are elevated sources. Okay. So we have to see that we, in this equation, we modify the equation for the source which is not here, but somewhere here. Okay. So in this case, to modify that, there is some few things we need to define. Okay. So if you, let me call this as H, okay, okay, and this thing, okay, what is this? This portion, it little rise in the plume, okay, because of because of the thermal buoyancy and other things that we'll discuss. So there will be, and this I am calling this as delta H, okay, and the overall height through after which the dispersion is taking place, that we call as capital H. Okay. Okay. So if I, whatever I have written here, if I let me write them in the words, H is nothing but H, small h times, okay. This is what we call as the effective stack height. That is equal to small h is the physical stack height. Plus delta H is what we call this as plume rise. Okay. We'll talk about plume rise little later. Okay. But the plume rise will have two components. One is a momentum plume rise like a jet action, and another portion will be the thermal buoyancy, because the gases that comes out, that is at the higher temperature, but that we'll discuss later. Okay. So what I want to do is modify this equation, okay, and say the source is not, the height of the source is not 0, but this is at h. Okay. So how do I modify this equation? Z is replaced by Z minus H. Does that everyone see that? Okay. So let's do that, and I'll write that equation again. So C equals to Q pi sigma y sigma z u exponential minus y square by 2 sigma y square plus, for z I must write z minus h whole square 2 sigma z square, and this becomes, right. But there is a slight little bit more change in this one, okay, and that change is that you put 2 here in front. Okay. This 2 has come from the way we estimated or calculate the constant k. Okay. In constant k, you remember that we derived the value of constant k. Okay. So if you derive the constant k under this situation, this k, that was the constant, which was, if you recall from your last time, that we defined the k, which was the large k. The new k new k for the situation when I am putting z equals to z minus h, that comes out to be the k that we saw yesterday by 2. So you see here the additional 2 has come. We are not discussing how that 2 has come, but then you accept that the additional 2 will come. So 2 changes from the equation that we derived yesterday, half or divide by 2, and z becomes z minus h. Okay. So that part you can see it very clearly. When the sources are elevated, some more things to be observed. Let's see. Okay, this is my ground level. At this point, at some point, okay, the plume is likely to touch the ground. Let me call this as point I. Okay. At some point, the plume is likely to touch the ground. Let me call that point A, point I. And don't forget this is my x direction. Suppose I am plotting the concentration, okay, at the So you see here the concentration at various values of x, and this is my stack height is somewhere here. So I am just taking that as a center line. So if I am measuring the concentration in the z plane, so that concentration will look something like this. Okay. Then I can measure here, it will look okay. When I measure here, I think what we'll do is we'll make it a little lower here. Okay. When the plume is reaching I, okay, when the plume is reaching I, and the plume hits to the ground, okay, there is a possibility that plume will be reflected back, right. The plume is coming and then it could be reflected back. And what has really been found, that sometimes the concentration profile looks little flattened here, slightly at the ground level, because once it is reflected, the concentration will increase. Okay. So that part some people have observed that this is what is the thing. Okay. So and then suppose I again see it after some time, little very far away, you may find this is my center line, that it should be like this. It may become more flattened, okay, because there is again thing might be added up this thing. So somehow in that equation we have assumed, in this equation or the equation which I wrote earlier, that ground reflection we had not considered. So we have to consider the ground reflection also. Okay, that how much could be the change in the concentration because of the reflection from the ground. Okay. Okay. Then how to account for this? Let's see. The best way to do this one is to think of, let's see if we can use another color here. This is another source here. We think there is an imaginary source underneath the ground. Okay. And this is also causing, giving you the concentration. Okay. So this source at the ground level, below the ground, this will have some center line. Okay. And the plume from here will go like this. It is exactly the mirror image. Okay. Exactly the mirror image. So here you see this particular source, okay, is not contributing anything here at the ground level. It is not contributing anything here, but you will see here that it is contributing something here. Okay. So if I draw the real the profile considering only one source of this particular source, my profile looked like this. Okay. And if I draw the blue picture, the contribution from this source, okay, will also be, or this might slightly go like this, and this source may contribute. All hypothetical, okay, but you see here the concentration. Okay. So you have to add the concentration given by the yellow graph and the one which is given by the blue one. So finally the picture, when you add these things up, will look like this. So it's not reducing asymptotically, but it is something reducing like this. So you might have slight addition of the concentration in this range. Okay. And I must account for this change. Okay. I must account for the reflection of my plume, okay, and that I am accounting for as if this is inverted source. Okay. I can write the same equation for this particular source, okay, by putting z equals to, in this equation, by putting z equals to, earlier we put z equals to z minus h, right, for this source. I can write the equation for this source by putting z equals to z plus h, okay, and I can write that equation, and I can add those two equations and I can get the concentration here, right. You have one source contributing, you have another source contributing, superimposing both of them and adding that thing, okay, and I can find out the net concentration by considering the reflection part. Simple thing, but well, we have to understand. So does everyone understand that? That I can write same equation what you wrote, okay, place z equals to z plus h in this one, write 2 here, and then contribution from this one plus this one, and then whatever the final equation comes, that is what I am going to write, okay, and see if you agree with the equation what I write here. That will be the considering the reflection part. I'll write that one. Okay, let me see if I can modify this. So the 2 should certainly come. Okay, let me see. Okay, then a large bracket, exponential minus z minus h whole square by 2 sigma z square plus exponential minus z plus h whole square by 2 sigma z square, close this one, okay, and close. Okay, you can work out and see if you're getting the same thing as I would get. Okay. Right? Okay. After considering full reflection from ground. Okay. Some of you have been able to derive, and that you get the same concentration. So this is what, in a broader sense, this is my general formula, okay, and that's what is the thing which I want to use depending on the situation I have. Okay, what is that we want to do? Some more changes from here. Okay, many times, or rather most of the time, we are interested in the ground level concentration because that's where the people live. Okay, so our interest sometimes is interest. Okay, so this, if you agree, this I can this one now write. C is a concentration at x, y, z. Put semicolon. This is how it is written. So a coordinate system x, y, z, and from a source which is at H. Okay. Okay. Few things I should tell. Okay, and then rather you should tell me. This u, okay, this u we took this one as the wind speed at ground level, right? Now this u should be at what height? Should it be still be at the ground level or at some other height? At H, because this is the wind speed which is affecting the plume. Okay. So earlier we took this as a ground level. So now you can make a note here. This u, okay, is at H. Earlier when the source was at the ground, u was at the ground level. Okay. So this u is it the mean wind speed affecting the plume. Okay. Where is my plume? My plume is at H. So my u should also be at H. Okay. Okay. Now some variation of this one, I will very quickly want to do this one. Sometimes I am interested in only ground level concentration. Okay. I am also interested in at the ground level, okay, what value of y you expect concentration to be more. See, we want to see the maximum impact. Okay. So we say, well, maximum impact where? At the ground level where the people live. Okay. So what do you think, again qualitatively, okay, the plume is going, so what level of y you expect, or what value of y you expect the ground level will be maximum? Y, I am asking y. Z is 0, because the moment I am saying the ground level, it means Z is 0, that goes automatically. Okay. As I am increasing, just see here, as I increase y, doesn't matter plus or minus, what will happen? My concentration will decrease. Okay. Maximum concentration will come when y equals to 0. Okay. That means you are just sitting, you are just standing right underneath the plume. Okay. The y's are 0. Okay. So plume is just passing over you, and then you think, well, it might affect the ground level. So many times we are interested in the ground level concentration. Okay. But I won't call it maximum, but when y equals to 0. That is our interest. You know, suppose the plume was passing over the IIT Kanpur from Panki power station. Then I want to say, well, what is the concentration to the people sitting at IIT Kanpur taking y equals to 0. Okay. So that is simple thing what you do here, you put y equals to 0 and z equals to 0, you come up with another expression. Okay. And that expression is most commonly used. Okay. Because that is where we want to find out when ground level concentration, that is when z equals to 0 and y equals to 0. Okay. And that thing you can very quickly see, this term will disappear. Okay. This will disappear. This will become h square. This is also h square. So it will become 2 times exponential h square by 2 sigma z square. That 2 will cancel out with this 2. So I will write that one, if you agree. The C becomes Q, okay, pi sigma y sigma z. U exponential y should disappear, minus h square by 2 sigma z square. That is all. Okay. That is all. Okay. Let's see what is that I want to cover in some sequence. Okay. One thing I want to remind you, and which is very important, and if you keep that one, you will not make much mistake. Always remember and underline that your x direction of the coordinate system, okay, x direction is always underline this. In this system, my x direction or the x coordinate is always the downwind direction, because that has been the assumption all through. Okay. The moment wind direction changes, your coordinate system changes and x changes, right? So that you should be careful. Okay, that is a very important thing. So now let's talk as to how we can use the equation, use the model if you like. What you need is certain things. Q. Where will the Q come from? From emission inventory, right? You remember we worked out the emission inventory. This is the source, this is a power plant burning so much of the coal, and with the sulfur content of this one, that coal consumption per day so much tons per day. So what will be the sulfur dioxide emission? And that you did in one of the examples, and you found out that the emission of sulfur dioxide will be 19 times the S, that is sulfur content, times your tons per day of the coal used and things like that. So that Q can be estimated, or Q will most of the time it will be given to you, or you can estimate given the data. Okay. The other thing which you need to know is U. Okay. Where will you get, how can you get this U? Okay. You cannot get this U so easily, but what you get the U is from the ground level measurements. That if not, you can at least go to the airport and find out what is the U in that area. Okay. But this is what the U they will give you, is they will give you the surface wind. No one will be able to give you very easily what will be the wind at the edge. Okay. Wind. So this one we need to answer. Okay. But we'll answer it a little later. But other thing you need is sigma y and sigma z. Okay. So we'll little bit have the discussion as to how and where the sigma y and sigma z they come from. Let's see what are these things and how we can measure them. Again, let me draw a picture of your chimney. I take the section at AB, and if you see the section so this is, what direction is this one? Y. Good. And this is my Z then. Okay. Y. And this is my Z. Okay. So what, and if I can, let me see if I can draw how the concentration will be seen in the Y and Z direction. So suppose if I keep on measuring, suppose I flew in the aircraft, okay, and start measuring the concentration at different places of Y, right, okay, and at different places of Z. Here my Z is whatever the value of Z is not changing at this axis, and I went on to measurement here, went up there and inside the plume, okay, and then I'll get a concentration profile, okay, Y equals to 0. People have found that this is a Gaussian kind of concentration. Okay. I can also within the plane, or rather not the aircraft, but with the kind of a helicopter, if you like, the thing. I am not changing my y coordinate, but I flew my helicopter vertically up and down and do the measurements at different heights. Okay. Then I will get a profile which will look like this. Okay. And what is the Z here at this line? what is the Z here? What is the value of Z here? This is capital H, right? Obviously, this is my capital H, and you see Z is my capital H. So don't put Z equals to 0. Okay. So I can find out the Y, and so this is what is the concentration at a fixed Z and by varying the Y's. And here my Y is constant and I am varying the Z. So this is my Z, which is equals to H. I will try if I can draw this one. Not so easy to draw, but let's see. If this is my Y plane, so I am measuring this is my Y plane, okay, and my Z plane will be something like this, and if I have to plot in the Z plane, that will look like this. Okay. So if I have done this concentration sigma Y and sigma Z, but that's the same thing I have drawn here. So if you, wherever is a distance where you get this as the 1 sigma Y, 1 standard deviation, okay, and here you will be some point where you will get okay, this distance, okay, where concentration is equal to 1 sigma Y, this distance, okay, is called sigma Y. Okay. The distance, okay, when concentration is equal to 1 sigma Z, that distance is called sigma Z. Okay. And remember that sigma Y and sigma Z are not the concentration but the distances. Okay. We again write that sigma Y and sigma Z are distances where concentration is 1 standard deviation. So having said that, now the thing is we have only explained this one, but we haven't said that how these are measured. Okay. The first attempt to measure sigma Y and sigma Z was at I hope spelling is correct. At TVA there was a power plant, Tennessee, USA, there was a power plant, and power plant was located in a plain terrain and things like that. And something what I said, that they didn't measure the sigma Y, they didn't measure the concentration at different this thing. Okay. So, but what they had was a ground level source, if I recall correctly, and then they various places of Y, they measured the concentration, and at different x's, okay, x equals to 500 meters, they measure the concentration, 1000 meters, 1500, and so on and so forth, and they plotted your concentration here. They plotted the concentration here, and then find out the sigma Y. sigma y as function of x, sigma y as function of x, sigma y as function of x. Okay. Similarly, they did the measurement for sigma z, okay, at various heights. Okay. So, of course, we do not have to get into the details, but you see these were actually measured. Okay. And what else sigma y and sigma z will depend on other than the x that we are seeing with the x? Okay, tell me, with sigma y, with x, sigma y will increase or decrease? Increase. Okay, so that is one thing is clear. So because plume is expanding, so sigma y is increasing. Okay, okay. What did I ask you? Sigma y will increase. Okay. What else the sigma y will depend on? Turbulence, and turbulence we are indicated by the atmospheric stability. So what they did, they ran this experiment by releasing some tracer. Okay, because suppose you are doing with sulfur dioxide will always be in this area by some other source, and results will be a mixture of sulfur dioxide from various sources. So they release some tracer, okay, some tracer, so that the tracer is not there in the atmosphere, so they can accurately measure. So they go on to the fields with some small handy gas chromatograph or whatever that instrument, I don't know, but they measured at different places of y, and they have to measure at the same time. So suppose they measure at 10 places, or maybe 10 people can stand with their monitor, okay, with gas chromatograph or whatever, and then they release some tracer. I don't know what tracer they release, but normal tracer that we use in air pollution study is SF6. So these are the people, and the person involved was the same person who talked about stability, that was Turner and his team. Okay. And then finally, once they come up with this data and all and things like that, they plotted the sigma y and sigma z. Okay, let's see. So this side is the downwind distance x. Okay, this is your logarithmic scale, okay, 10, 100,000, 10,000. And this is in meters. This is sigma . And they are the, since I am drawing, they are approximate, but you can get in the book exact numbers. Okay, so they reported this to be something like this. So this, they reported this for the stability A, B, C, D, E. Okay. So whatever your distance is, take that distance. Suppose you want to find out 1000 meters from the stack. You know the stability. Let's say stability was D. Corresponding value of sigma y can be found out from the graphs developed by TVA. Okay. So let's say you want to find out, let's say at 500 meters, and your stability was C. Okay. The sigma y value could be 100 meters. Okay. This is not an accurate, but this is how you use this one. Okay. Similarly, they did for sigma z, which looks a little bit more. And by the way, don't forget that this side is also log scale. So 10 100,000, 10,000, okay, 10, 100,000, okay. So they here for sigma y the lines were straight, but here they got the curved lines and things like that, and then this is your A, B, C, D, E and F. That is your stability A, B, C, D, E and F. Okay. All right. The same thing at what distance you are, you can find out what the sigma z will be. Okay. See, I have the graphs, okay, but I didn't bring the laptop and things like that. So this particular graph, some of you in the front up can see, okay. This axis is downwind distance, x, and this side is sigma y, okay. And these are the value of sigma y for stability A, B, C, D, E and F, okay. That's something which I have plotted here, okay. And then same thing for sigma z, and sigma z you see here more curved graphs, same downwind distance on the log scale, the value of sigma z on the y axis, but again log scale, and you see here A, B, C, D, E and F, okay. You can find out as to what will be the value of sigma y and sigma z depending on what x you are interested in and what is the value of turbulence or what is the value of the stability class. I'll just quickly pass on this one to you. It is all there in the book. There is nothing which I am teaching which is not there in the book, and you can all have a look onto this one to show you as to how you can find out the sigma y and sigma z for given the value of downwind distance. X is what, again remember, x is a downwind distance, okay, and you can find out the sigma y and sigma z, okay. Another thing which you should note, and I'll write that so there is no confusion. Was 10 minutes, okay. Then the person stood there for 10 minutes taking the sample. So that was the 10 minutes. So essentially by using these sigma y and sigma z graphs, you will be finding out the 10-minute average concentration, okay. So far, any question? If you are given the Q, if you are given the U at the height h, and you are given the h, you can find out the concentration at different locations, okay. So we'll talk about, okay, let's see one more thing, okay. Then what happens once you have a graph, then it's a normal thing to fit an equation, because graph cannot be put into the computers, right. So the people have fitted the equations to this one, and there are so many formulas that have gone, but this was the basic work, okay. So now people have fitted the kind of equations to this, generally in the form of sigma y equals to so if you don't want to use a graph, okay, and A, B and C, D will be function of, they fitted the curve, will be the function of stability, right. If stability is for the same x, if stability is different, then sigma y is different, right. For the same x, stability is different, then sigma z is different. So that numbers I'll give you, or maybe I'll pass on through the mail to you, rather than giving and spending some time. So there are many more other formulas are there that I'll probably will put a slide in next time to show you how the sigma y and sigma z can be calculated without using these graphs. So graphs were fundamental. Okay. The other thing you need to know is the before you are set to use that equation, you need to know the Plume rise. Okay. And that is will not derive delta H, but I'll give you again some formula in some ways. Okay. That is enough for us for the time being. There are many things for delta H to find out. One of the ways is to using the okay, let me write that. And U is we should write the units here. U is the wind speed at small h or big H? This is at small h. What we are saying that this particular wind is affecting the plume rise. See, when wind is there, something wants to rise and there is a horizontal force, so that will affect the wind. So there will be no wind rise. So again, why I am asking you is this U is where? Not here, but this U is at H. Okay. At H or stack tip. See, these are little small things, but it can make the difference. Okay. So this U, okay, is at the stack tip, and that U which was in our formula was at H, because that is what is the mean wind which is disturbing the which is causing the advection in the plume. This U is causing the problem or disturbance in the plume rise, because we are discussing plume rise. Okay. Since they are constants, so you have to use the same units. Okay, you can't change the units than what I have written there. Okay, and most important thing, people make mistakes sometimes, is the pressure which is always in millibars. Because we have done some changes and we got some constants and things like that. So P is the pressure, atmospheric pressure in millibar. Okay, millibar, normally how much is the millibar is the pressure? Around 1000, 1100, 1200, 1000. That is a normal millibar pressure. And there are there will be some more changes here. We apply some factor here. That factor, we will discuss that one in the next class. That factor takes care of the stability, because here we have not talked about the stability. Okay. And one more thing, maybe we can talk later, but this component 1.5 times Vs times d into U, this component, okay, or this term will give you momentum rise because of the jet action. Okay, because of the jet action. Okay, this component Vs d U times this term give you the thermal buoyancy. Maybe I'll write it, in the next class. The two components of the plume rise, momentum rise and the thermal buoyancy. Okay, some plumes are dominant in terms of the momentum rise, some plumes are dominant in terms of the thermal buoyancy. Okay, we'll see what it comes out to be. Okay, I think we'll stop here and try to do some. I still need to define how you can find out the U at different heights. That we'll talk later, and maybe we'll start some example to get the feel as to how the things are done. Okay, we'll stop it here.